Okay, so now we're going to see in this example an example of how Taylor series is used in Engineer to kind of make things simpler. Now it seems like this is all very complicated. It's not making things simpler, but ultimately what the Taylor series is doing is approximating very complicated things. The reason these are complicated is because they're inverse functions using addition and multiplication. So that's why this is good. And so what you can do is if you solve some equations and say, for example, you get a sec term in it, as you do with various different beam equations, which are beam situations, beam formulas. Let's see, I'll have a look at one. I actually don't know where this formula comes from, but I found some other examples. See this one here. So it can be shown that if you have a column and you exert a load at it slightly off the middle, that this is the maximum horizontal deflection. And this isn't really the formula that you'll see in your whatever your Euro codes. You'll actually see this formula. And so what you see in a lot of the engineering formulas is they're only approximations, but like you can't be going around with a sec is basically the idea. It's just much easier to deal with this. And these are good approximations. I mean, we've seen pictures where it's good. Okay, so let's see an example here. So the maximum deflection of a beam of span L. Now there's no and this is exactly, so it's the exact formula. M squared is given by this. Simplify the formula using this Mclaren series. Now deriving the Mclaren series for sec of x would be the first part. Have I any question that asks us to do that? No. So maybe it's a good exercise for you to do this exercise. Okay. Show this. So the first two non-zero terms of the Mclaren series, sec of x to 1 plus half x squared. Okay. So what we're going to do is, see this sec of ml over 2, we're going to approximate it using this. So sec of ml over 2. So what we're using is the fact that sec of x is approximately 1 plus half x squared. And we're going to use this at x equal to ml over 2. Now this x would have to be small, and it probably is small because m squared is p over ei. P is probably measured in kilonewtons and ei is big. So it's a number, whatever, divided by a big number. This is a very, very small number. And therefore, small number by span over 2 is still small. So this approximation is going to be accurate. So if I use this formula, I get 1 plus a half, and then my x here is ml over 2. I need to square that. And I just have a little bit of algebra here, right? So I have 1. Now think about what squaring means. So I got ml over 2 by ml over 2. So I have a half by ml over 2 by ml over 2. And if you know how to multiply fractions together, you do multiply the tops together and then multiply the bottoms. So the top you got 1 by ml by ml. The m by m gives you m squared. The l by l gives you l squared by 1. And then on the bottom you have 2 by 2, and because it's squared, 2 by 2 by 2 is 8. And now I think what we're going to probably, we'll leave that there for the time being. So what we see is delta max, which is equal, this is exact, WEI over P times sec of ML over 2 minus 1. And we're going to use this approximate, we're going to approximate this with this. So this is approximately, and use some space here, WEI over P. And then let's replace this in here, 1 plus m squared L squared over 8. That's approximating this bit, replacing it, minus 1. The 1 minus 1 is gone, and we're left with WEI over P, M squared L squared over 8. And then what is M squared? It's P over EI. So you get WEI over P, and it says that M squared is P over EI, and you still have an L, and you still have an 8. And what happens? The P over P is equal to 1, so that's gone. EI over EI is equal to 1, so that's gone. So you're just left with, sorry, that should be L squared, W L squared over 8. And maybe that's a familiar formula to you. So this assumes, it's written there, that this thing is approximately small, which it is. Okay. So, yeah, there's some exercises there. Now, the only thing we've done here is that we've gone close to x equal to 0. You don't have to go close to x equal to 0. You can do this near any point. And when you do it near any point, that's called Taylor series. So what is the Mclaren series of log of x? Okay, first of all, Mclaren series says what's going on at 0. And if you do log of 0, it's undefined. So this example shows that not all functions are analytic near x equals 0. Well, log isn't even defined. However, suppose that a function is analytic near the point x equals a. It turns out that if we write f of x equal to, now just to be, I would normally write a0x plus a1x, sorry, a0 plus a1x plus a2x squared plus a3x cubed, etc. But I'm going to do x minus a instead of x. So if you write this out, now the a is some point plus order x minus a to the 4. A is some point alternative to 0. So for example, you could do the Taylor series of log of x near x equal to 1. So this is supposed to be accurate for x approximately equal to a. Okay, so if this works, then the formula, it turns out, is given by this thing. Okay, so the Mclaren series is just a special case of the Taylor series about / near a equals 0. So we'll do one example that will just do mostly just be some more differentiation for us. So find the first 3 terms of the Taylor series. It doesn't say anything about non-zero, about the point a equal to pi over 4. So we need to calculate first f of a, f of pi over 4. So this is sec of pi over 4. Sec is equal to 1 over cos. And as we see from the question, cos of pi over 4 is 1 over root 2. So 1 over root 2. Now, the way to handle this is multiply above and below by root 2. If you don't, or there's other ways, you might just go into the calculator, whatever, you get root 2. However way you look at this, maybe like this, maybe I'll just do it here. 1 over root 2 is equal to root 2. Yeah. Then we'll go to the first derivative. So the first derivative of x. Now the derivative of sec, I probably have to give to you in a question. I know in this, it's probably in the big tables. I might send you on a big tables in the weekly summary. I might give it to you, look, we'll see, sec of 10. Sorry, not sec of 10, sec by 10 is the derivative of sec. And we're interested in this at x equal to 0. Sorry, not x equal to 0, x equal to pi over 2. Pi over 4, sorry. A bit tired. So we get sec of pi over 4 times tan of pi over 4. Sec of pi over 4 we've just calculated is root 2. And tan of pi over 4 is 1. So we get root 2 by 1, which is root 2. And now we go to the second derivative. We need to differentiate sec by tan. Your best bet there, probably only bet, is to do a little product rule, u and v. probably have space to show off a product rule here if maybe you're a bit lost earlier. So the product rule formula says when you differentiate a product, you do the first thing, which is sec of x, times the derivative of the second thing. Derivative tan of x in your tables or whatever is sec squared of x, plus the second thing, which is tan of x, times the derivative of the first thing, which is sec of x tan of x. So I'll just write down, that looks a bit bonkers, but look, the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing. That's what the product rule says. We're interested in this at x equal to pi over 4. So sec of x at pi over 4 we've calculated as root 2 times, now this would be sec of pi over 4 squared, root 2 squared. What's root 2 squared? Square root of 2 by square root of 2 has to be 2. You know, you might need a bit of calculator to help you. Plus tan of x, tan of pi over 4, well, tan of pi over 4 is 1, times sec pi over 4 is root 2, times another tan of pi over 4, which is 1. So I get 2 root 2 plus another root 2 is 3 root 2. If you have to go into the calculator, that's okay. I would like you to avoid rounding in this chapter unless it asks for it. We're going to talk about rounding next week. Okay, so now using the formula, we have now if we cut this off on the first 3 terms, which is what we're doing, this isn't an equals, it's an approximation. So sec of x, and by the way, if you remember I said, oh, as an exercise doing the Mclaren series of sec, well then you just be plugging in x equal to 0 into these, and you get your sec of x near x equal to 0 is approximately 1 plus half x squared. Anyway, sec of x using the formula is approximately f of pi over 4, which is root 2, plus the derivative, I'm using this, the derivative at pi over 4, which is root 2, times x minus a times x minus pi over 4, okay, plus the second derivative at a, so the second derivative of pi over 2 is 3 root 2, divided by 2 factorial, which is 2 by 1, which is 2, times x minus a, x minus pi over 4 squared, which is valid for x suitably close to pi over 4.